So now we are going to look into some more technical detail in TEM, and we are going to talk about some specific terms in case of imaging when we use a transmission electron microscopy in this lecture 15. So before we actually start, the main important part of using the electron microscopy is the wavelength of electron. And the concept, I think we already know because we have studied this a number of times, that the wavelength of an electron is basically dependent on the accelerating voltage. This relation might be already known to you because you know that from de Broglie wavelength lambda is equal to h divided by p, and if you basically consider momentum, you can actually write it down in terms of h divided by root over 2 me. Okay, if you use that p is energy is equal to half mv square. Okay, and then we already know that energy is nothing but if we apply a voltage and there is a charged particle, then ev will be the energy. So this e is nothing but e into v. So basically this is the relation that we have for the wavelength, and depending on this we can look into the factors that the Planck's constant is something which is already known to us. The mass of the electron is fixed, the electron charge is fixed. The only thing that we can usually vary is nothing but the voltage, and if we can vary the voltage we can actually manipulate or play with the wavelength of the incident electron. If we are actually thinking of observing a very small region with a very good resolution, this wavelength must be as small as possible. So what happens is, if this V or the applied potential is high, the wavelength will definitely be less. Okay, so that is what is applicable here. So if we just put in all the values, the final relation that we have is lambda is equal to 1.5 by root V nanometer. So you should remember this result. Okay, sometimes it is asked. Okay, and this voltage is varied from 0.5 to 3 into 10 to the power 4 volts. So if the accelerating voltage is high, the wavelength is small, and the electron will actually achieve a very good resolution. So it depends on the requirement that these things are adjusted. Now if we look into the type of images that we talk about, there are three kinds basically. So number one is the bright field imaging. So this is something which is the bright field imaging. I'm going to discuss one by one. Okay, but then in very normal sense we can say that bright field imaging, it means that we are going to get a bright image. And if we consider something like a dark field imaging, the region around the sample will basically get darkened out. So wherever the electrons are getting incident is darkened out, and the region where their electron is not falling on the detector, it is bright. Okay, so that is basically called dark field imaging. And then we have got something which is called the diffraction images. Now if we go and focus into a particular region, okay, then the crystal structure can be actually observed, and if the system is more or less crystalline in nature, these kind of images can be seen, which is basically called the diffraction images. Specifically they are also called selected area electron diffraction, SAED. So we're going to look into these things now. But before, let's first begin with, before that we begin with bright field imaging. The bright field imaging is the most common image generated. So if you look into any kind of research paper, and if you look into a TEM image, you'll more or less look into a bright field imaging until it is done deliberately to enhance or study some other or closely the samples. Okay. So some areas of the sample will scatter and absorb electron and therefore appear darker. So if you remember, in the last class I told you about a mesh or a lattice which is actually connected with let's say a window, and you are shining a torch on it, and the lattice points basically will appear dark on the screen. So here also it's the same. In bright field imaging, what happens, the area of the sample gets scattered and it basically absorbs the electron and therefore appear darker. So which absorbs electron, those electrons actually cannot pass through the sample, so that will appear dark on the screen, and the other areas which are actually transmitting the electrons will appear bright. So basically what happens is the image will appear as a shadow of the specimen. So whatever you see is a shadow, okay, which will be a combination, or the entire image will be a combination of the electrons which are absorbed and the electrons which passes through. So in bright field image, the objective aperture, so we have seen the construction of a transmission electron microscope. So there the objective aperture is basically used to select the unscattered electron beam. So more importance is given to the unscattered electron beam, because these electrons will fall on the photographic plate and form a bright image. And in doing so, the scattered electrons are excluded from forming the image. So whichever electrons are getting scattered or getting interfered by the atoms of the system, okay, or the structure of the system, which gets absorbed, the electrons, that is actually not considered in the imaging part. In the imaging part, only the part is considered which the electron which directly passes through the sample. So as a result, the final output or the final image that we actually get will be a combination of the shadows also as well. So this aperture enhances the contrast in the image. So this will actually enhance the contrast. So you know, contrast, if we have something dark and bright, we can adjust the contrast in a proper way, except all the bright electrons which are falling on the sample. Okay, so then basically we are actually getting a very contrasting, good contrasting image. So the dark field imaging is just the opposite. What we do here is that the electrons which are passing through are not considered in the image. The electrons which are getting absorbed by the sample are considered in the image. Okay, so you can basically consider it to be a negative. Okay, negative. So what happens is, by excluding using the primary aperture, so here we use the primary aperture, the unscattered beam from the image collected below the sample, and the image is produced by the scattered electron. So only the scattered electron is used. Okay, and that's why it is also called the selected electrons. Okay, so selected electron imaging is also a term which is often used. So the regions where there is no scattering occurs, such as where the primary electron beam passes straight through the sample, appear black. So that is not considered for the imaging. So the straight electron without interacting with the sample will be considered as black. And this kind of imaging is actually very useful in studying the crystal defects. So if you get any kind of defect, that can actually be studied by using this kind of imaging. And of course, for the imaging of the specific crystallographic phases. So if there are some phases which exist, that can also be studied using this. And finally, the third type of imaging is called the diffraction images. As the term suggests, we already know what is meant by diffraction. So the electrons is not that it will be absorbed or it will be just passing through. There will be electrons which also be diffracted. So the result of backscattering as the beam passes through a crystalline sample. So diffraction, scattering, okay, in general we can say that diffraction is a special form of scattering, only that it has got some kind of direction into it. So we have the crystalline sample and the Bragg scattering, if it can be followed. Okay, we already know about Bragg scattering and Bragg's law and all. Okay, we actually get the diffraction images. So if we consider a selected area diffraction aperture which is inserted to delimit the region of interest, we basically take a very small region, okay, and then an image is created below the sample, and this region is basically called the back focal plane, and it is basically seen as an array of dots. So as I have shown you here, okay, this is basically looked something like this, as an array of dots. Okay, so this informs the viewer about the crystal structure of the sample. So if you basically have got a very crystalline sample which has got long order arrangement of the atoms, okay, basically it will show these kind of dots of the diffraction pattern. So if you basically consider a normal idea about diffraction, we basically have the electron beam which is incident on the sample, and let's say the sample is more or less crystalline. This will be diffracted at each of these planes, and these diffracted waves will actually basically come out of the sample and will form an interference pattern. So we have to look into this factor. So this diffraction pattern will provide information about the crystalline nature, and if we have a crystal lattice, it will act as a diffraction grating. So you know about grating and slit. Okay, so if you basically have a very small opening, it is called slit, and if you have got a number of small opening, this basically combines to a grating. So if we have a sample and we have the atoms arranged, the diffraction can occur at each of these points. So it basically combines to form a grating. Now the interference pattern are produced in the electron beam as it travels out of the lattice, and that can be projected as an image of regular dots or rings. So whatever projection we get is nothing but the interference pattern. So if we look into some more research paper, you will see that there is another kind of diffraction pattern which is observed, which looks like more or less like a ring. So this sample might be a single element, okay, it can be a nanomaterial or it can be a compound which is having a combination of different kinds of material, and based on this we'll be getting these diffused rings as such. So this actually points to a different thing altogether. So sometimes what happens, the intensity, instead of the intensity spot, the electron diffraction pattern is composed of concentric rings like this, and the material that contains no long range order in the atomic lattice will produce these kind of diffuse diffraction pattern. So if there is, the material is not very crystalline and there is no long range diffusion pattern, it will actually form these kind of diffused diffraction patterns, and there will be no distinct points as such as I've seen in the previous image, and no discrete reflection, and there will be possibly 2 or 3 diffused rings which will appear. So in this case what happens, most of the time this is actually shown by amorphous sample. For example, if you have some polymers or metallic glasses, this will actually produce these kind of pattern. So there are some important points to note here. You basically have this, which you see most of the times. This is actually called the beam stop. So if the central point is very intense, the diffused rings are usually not observed. So this image or this pattern or this beam stop is usually used to cover the bright central beam spot, so that more diffuse ring can be captured as a digital image. Okay, so that is what we do. We don't need too much brightness. If we have too much brightness, then definitely we cannot differentiate what is the diffuse ring looking like. Okay, or if the diffuse rings are present. Now if the material is a collection of a large number of crystals, so we have different samples with different orientations as such, then the individual reflections are seen within the rings. So we can see a number of reflection, and the more and more rings will appear if their compound contains more and more elements. So this kind of imaging is called selected area diffraction, or selected area electron diffraction. Okay, SAED or SAD, both are valid. They use different terms. Okay. So that's all for today, and these are the images that usually get as an output from TEM. Okay. So this is all that we are going to look into for TEM. Please remember, before I end the class, whatever we have studied for XRD, SEM, TEM, until and unless you do some experiment on your own, do the analysis on your own, probably everything will be theoretical knowledge. So it's very important that we should know what kind of software we can use. So in the coming presentations we are actually doing that. So I'm hopeful that all of you will try to learn something from your end, and definitely in the next semester or when you are doing your project, will help you out with your different schemes of studies. Okay, basically what software you use to do XRD analysis, how do you analyze the ring pattern, and so on. Okay, but let's be interested enough to learn the different kinds of software and how to basically characterize the sample. Okay? That's all for today. Thank you.